Unlike the previous talk, I'm going to be talking quite a bit more technically. We've been working over the last few years on building mapping extensions to one of the new NoSQL databases that's been very, very popular. And I think that most people here have probably not heard of Neo4j, so I want to introduce it briefly before talking about the mapping data. Starting with, Mons Adler this morning mentioned that you don't give away your mushroom picking spot. That's a secret. And anyone here has heard of Peter Neubauer? I think there's a very good chance. Yeah, I see. It's about 70%. I'm not surprised. Peter Neubauer must be one of the most connected people in Sweden. Anyway, he's the one that got me involved in this field. And a few years ago, while building the system, I challenged him to see if he could find my secret mushroom picking spot. What we see here is a picture of my daughter with a very nice large Carl Johan swamp. And it's technically possible to find my spot if you were able to data mine the OpenStreetMap data. And there it is. Honestly, I'm not actually going to tell you where it is. That would be no good. But it is possible to analyze OpenStreetMap and find out some interesting things that you might not be able to see simply looking at the mapping data. So towards the end of this talk, I'll show you the structure of OpenStreetMap and how we can actually analyze it very briefly. We don't have very much time. Starting with the graph database. I mentioned that this is a new database. It's not a relational database that most people working with mapping data on the internet would be familiar with. But as you can see, here's a quote from the CEO of Yahoo. He's talking about all the different kinds of graphs that people care about today. There's social graphs and network graphs and influence graphs, many kinds of graphs. This is the modern world today. We care about connectedness. We care about the fact that everything is related, and this is the most important thing. This is not easy to model in most traditional systems. The sheer volume of data on the internet is not easy to model, and the complexity. In the last year alone, we see like 6 books have been published on this particular subject of graph databases. But let me explain what they are. First of all, volume of data. In the last decade, the internet alone has caused a massive explosion in the amount of data that's available. This is data of all kinds, including, of course, mapping data and location data. As a result, we've seen a whole new field of databases opening up called NoSQL, which really means everything other than relational databases. And this is because the relational databases don't scale as well. They don't scale to the insane sizes that we've got. If anyone's interested afterwards, I can explain why. I don't have time to go into that level of detail. But I promise you, it was needed to move away from relational databases. These 4 types, the one that you may be familiar with is probably the document database because it's most targeted at web application development. But it's not necessarily the best for what you might want to do, especially complicated data models. Let's explain in terms of data size where these position. The key store scales the best. It can go for extremely large volumes. Amazon, for example, uses this kind of a data model. If you need slightly more complicated data, big tables, like from Google, and then, of course, more complicated data, document databases. None of these are able to model the level of complexity that you might be used to in a relational database, the common databases like Oracle and SQL Server. However, the graph databases can. And this graph database that I'm presenting today was actually made here in Malmö, in Mink, just a couple of blocks away. That's where they started. Now they've got their main head office in San Francisco. They can handle huge volumes of data and huge complexity, which is a very nice sweet spot. Let's look at mapping on this. Key-value stores can only store points. Sounds okay. Big table, points. Documents, points. All of these have APIs for storing locations and only working out how close things are to each other, which is quite a common case, I agree. But relational databases, which are the industry standard, you must agree, can do a lot more. And so can we. Points, lines, roads, polygons, regions, intersections of regions, complicated geoprocessing. And what I think is one of the hottest things on the internet today is OpenStreetMap, crowdsourced mapping data. Jan Erik's going to talk about crowdsourcing as well, which is, I think, it's a very, very interesting area. We use crowdsourcing and we use OpenStreetMap a lot, and I think it's one of the most interesting things that's happening right now. A quick intro to the graph. I don't want to go into too many details, but imagine your database looks exactly like you would draw something on a whiteboard. If you've got a model of the actors in the Matrix movie, you're going to draw them like this. A couple of actors, who they know, who's enemies with whom, who influences whom. It's a very flexible model, but most importantly, it looks like the way you see it in your mind. Anyone worked with a relational database knows that's not the case there. There you have to normalize and write object mapping relations. It's quite complicated. This is a far easier model. Oh, I don't like text slides. We can skip this one directly and move on to some of the things we did. In the beginning, we published to desktop applications like this one as an OpenStreetMap model in the desktop. We moved on to web applications. And this example is particularly interesting to me. This is my hometown where I live right now. It's a small village in the middle of Skåne called Billesholm. And you can see it's got quite a bit of detail there. Every street, every park, every pathway, every cycle path, children's playgrounds, everything. The fun thing about this particular map is I took my phone 3 years ago with a GPS on it, and I cycled. I cycled the whole of Billesholm, I went back to my computer, uploaded the data, and I made this map. I added my data to a graph, a network of connected information that covers the entire planet. This has been built by tens of thousands of people all over the world. They've built a map of the world, and this map of the world is more detailed than what you will see on Google Maps, because people care about things that Google may not, or the government may not. They're not bothered to map. I've got a slide later on we probably don't have time to get to, but somebody mapped the tracks of a roller coaster. You wouldn't see that on Google Maps. And this is because it was important to that person. So crowdsourcing is, I think, totally changing the way people view with data. You're going to see more information than you would ever have seen before, and it's already true here on OpenStreetMap. The model, again, yeah, this is super flexible. I'm going to have to just hope you take my word for that, because we needed at least an hour for me to really get into the details of why this works so well. But this model is something that you can, if you're a mapping person, you can just go into it and understand everything, and it looks great. But there's more interesting stuff here. Let's move on to that slide. This looks quite complicated. What's really nice about this database and the way we deal with mapping data is, unlike any other database, we put the indexes and the mapping information together with your data model. You can all be analyzed together. So you can actually analyze your index, you can analyze your views, you can see it all as one big connected graph, which is incredibly flexible. In this case, the OpenStreetMap model's on the top right there. This is showing you streets and parks and how they connect together, how a street might lie along a park, where streets intersect with each other, and how to analyze. Here is our spatial index for searching for map data, and you can see it's connected completely in the same graph. This is not true of any other spatial database. All other spatial databases keep it as a separate issue. It's a black box, you can't touch it. And of course, other complicated things you can just add on to improve the power of your model. Routing. I talked to the people who wrote the routing engine for the most popular open-sourced mapping database in the world today, called PostGIS. And that pgroute model, it has to pull all the data out of the database and build an in-memory model in order to route. Put it on something softer. The reason for that, of course, is that routing is a graph activity. It's a connected network. You have to trace the routes of the roads in order to be able to find where you want to go. If you're here and you want to go there, it's a graph analysis. You can't do it in another database, because no other database has graph structure. In this database, you can actually trace the routes in the database, allowing you to scale to, you could route my path, by bicycle path from here to Moscow via Finland, for example. You wouldn't be able to do that in any other system. So that's a very nice feature of this. It's also more intuitive because of that. I mentioned at the beginning that everyone else does points and we do everything else. This ended up hurting us at one point because they said that our system was too complex for the average user. So we wrote a small API which allows you to do the simple location-based searches that everyone else wants. And here is a complete example, including initializing the database, loading data, and performing the search. The key part is just this point down here. Define my starting point, perform the search. 2 lines. So we've got this system as easy as you would see in MongoDB or CouchDB or any of the other systems. And this API is also exposed through the remote API as well and in the Cypher query language. So it's now very easy to use from any system. That's the result of this search. When I first presented this, it was 2 years ago. I tried to make a joke. Didn't work so well. I talked about a traveling salesman driving around Scorner, and he's getting really tired and needs to find a place to relax, so he does his search from where he is. And he... Okay, I got a better laugh this time than that. That's good. I'm going to end off with just a couple of slightly interesting examples. I think here is an application on an iPhone from Poland. They used Neo4j Spatial to do routing on an iPhone app, searching for places of interest from close to where you are. That was very interesting. So we provided a bit of technical advice to the guy, and he built this app. Very nice. This one, for me, I just did this myself. I wanted to analyze the contribution of people to OpenStreetMap, and I created an animation where you can see roads being built over time. This happens to be Cyprus. You run queries like that. We say, for this time slice, who are the most active users and where did they put their roads? The last example is, I think, particularly cool. We got contacted by a guy working for a theme park in the United States. It's not SeaWorld. I won't name the other theme park. He didn't allow me to, but he wanted to know how to do routing on a drawing. There's an artistic map of the theme park. How do you route? I know where I am on my iPhone. Where's the closest toilet or where's the closest coffee shop? How do you do that? There's no system that can route on a drawing. So what I advised him to do was the following. First of all, get yourself real mapping data, in this case OpenStreetMap. And this map doesn't look at all like the artistic map. It's the wrong angle, it's all distorted, everything's different. That's because the artist has drawn something that emphasizes places of interest, gives them more space, moves things around to fit on the drawing better. It's not geographically correct. So what you can do is try to line it up a little bit. And this is the map, by the way, where the OpenStreetMap users contributed the roller coaster. You can see the roller coaster at the back of that. Quite amazing. In Germany, apparently, they're adding every tree and fire hydrant. Germany's the most thoroughly mapped place on the planet. Unfortunately, I work a lot with China, and China is not, because you're not allowed to yet. But that's changing. What you do now is you take all your points of interest and you just correlate them, connect them in the graph. This is a graph. And the pathways, of course, you want to connect with a little bit more detail. So I've drawn the pathway of the bridge over the lake, and you connect it to the real one. You don't need every single point, but enough points that you could route. And then, of course, you'll be able to, your phone will tell you where you are in the real world, and you can show that on the drawing. And then you can say, where's the closest coffee shop? It can route it in the real world on OpenStreetMap, and then show it on the drawing. And bang, you've got yourself your iPhone app, which can show the artist drawing that the theme park really wants and provide fully fledged routing, which is very, very cool. I've got another example, but I think we're probably running out of time now. Okay. I threw this one at the end because this is actually what I do. This is my business. We work with cellular networks, so this is a little bit more technical, but what we have are apps that run on mobile phones, iPhone, Android, BlackBerry, Windows Phone. It collects lots of information about the network, about the user's behavior, accessing Facebook, how fast, how slow, what services work best, and of course we show it on the maps and we analyze it. So it's quite technical. This gets to a very interesting point. I'll jump ahead to one very interesting point. Why is this database fast? What we see here, those two tables are how you would model a cellular tower, the towers that you see around that you talk to with your cell phone. These towers are made of a tower plus antennas pointing in different directions. How do you model that in a relational database? That would be the tables. If you ask your database, tell me all your antennas for that tower, it gets slower if the database gets big. This is the reason why relational databases are bad for very large data. The order is order n, which is quite bad. If you index the table, index up here. If you index the table, you get order log n. It's still not very good. It's okay, but if you get very large data, you're killed. In the graph database, it's order 1. If you ask this antenna, this tower, what are your antennas? It takes milliseconds if you've got just 10 objects in the database or you've got 10 billion. It will take just 1 millisecond, exactly the same time, because the local search is independent of whatever else exists in the world. Same thing in the real world. If you're standing at a tower and you want to see the antenna, it doesn't matter if there's another tower in China. Who cares? But a relational database, unfortunately, is structured like that. Everything's in a table, you have to search it. This one is much, much, much faster. So for you, if you're interested in building mapping applications over very large amounts of data, global spanning, this is definitely the way to go. That's too technical. I think we'll skip that one. Well, then that's all from me. Thank you.
Thank you.